Hello, this is Dr. Viv. In this video, we shall investigate the work done by a force, or rather, try to define the concept of the work done by a force using some mathematical apparatus which I will first have to develop. And that is the scalar product of two vectors. We have seen how vectors can be added and subtracted. Now we are ready to multiply vectors. So let's just take in 3 dimensions two vectors. I'll call them A with x component ax, y component ay, and z component az. Alternatively, I can write this as ax I hat plus ay j hat plus az k hat, where I hat, j hat, and k hat are the unit vectors in the x, y, and z directions. Similarly, let's say that I have a vector b, which is bx, by, bz. The dot product, or the scalar product is sometimes called the dot product because of this dot between the two vectors. That's how it's written. Is simply given by multiplying the x components of the two vectors together and adding them to the y components and the z components. It is very important not to put a I hat, j hat, or a k hat here. That's one of the most common mistakes students make. The scalar product, it inputs two vectors. You take a vector, vector 1, and you dot it with vector 2. You produce a scalar. The word scalar simply means a real number. A real number which can either be positive or negative. There's nothing wrong with the scalar product being negative. We can actually write the scalar product. This is a Cartesian representation of the scalar product. The scalar product can also be represented in polar coordinates. In polar coordinates, it's a dot b is the length of a times the length of b times the angle, cosine of the angle between them. So I've drawn a little picture there to help you. The length of a and the length of b are defined in the usual manner using the Pythagorean theorem. So for example, the length of a would be written as the square root of ax squared plus ay squared plus az squared. And you can write a similar expression for the length of b. So that is the theory behind the scalar product. Actually, one of the useful things about the scalar product is you can actually find the angle between two random vectors. So just to put some bite into the theory, let's consider an example. And I'll do this in 2D to make my life easy. Let the vector A be negative 5 I hat plus 6 j hat. And let the vector B be given by 4 I hat minus 7 j hat. So my aim is to find the angle between them. Now, just by looking at it, you can't really tell much about the angle, but what you can do is find the dot product using the Cartesian formalism. That's just ax, which is negative 5, times bx, which is 4, plus ay, which is 6, times by, which is negative 7. 5 fours are 20, and 7 6 are 42, so I get negative 62. Meanwhile, let's also find the length of a. Length of a is going to be the square root of negative 5 squared plus 6 squared. That's 25 plus 36, root 61. And similarly, the length of b is going to be 4 squared plus negative 7 squared. So that's 28 plus 49, which is 65. So we can actually use the set the two definitions of dot product equal, and so I'm going to get cosine phi is going to be equal to a dot b divided by the length of A times the length of B. Well, we already know what A dot B is. It's negative 62. And then the length of A is root 61, root 65. And if you calculate this, I did it with a calculator earlier, the angle turns out to be 170 degrees. It might not be a bad idea to verify that this is approximately true by actually plotting A and B in a little diagram. So I'll do this quick and dirty plot here. I goes up to 5 and J goes up to 7, like that. So A is going to be here, negative 5, and then positive 6. So A is going to be something like this. Okay, it's a very crude picture. And B is going to be 4 and negative 7. So you can see that it that angle is basically 170. So one of the important reasons I drew this figure is to show you that there are actually two angles between two vectors. You have this angle that's smaller and this angle that's bigger than 180 degrees. The dot product or the scalar product always finds the smaller of the two angles. Now let's go on to the main purpose of this video, which is to use this mathematical apparatus to define the work done by a force. So far we have understood what a force is and how to draw a free body diagram. Now we'll enter the important concept of the work done by the force. The work done by a force, WF, is defined as the integral from the initial point to the final point of the force dotted with dr. Now in general, in 3 dimensions, dr is the Cartesian unit vector in a general direction. So you're going to write this as dx I hat plus dy j hat plus dz k hat. Basically what you're doing is you're differentiating the what's called the position vector r, which is given by this formula. You're differentiating by putting a d in front of all these 3 things. So that's the dr, and similarly the force F can be written as x component I hat plus y component j hat plus z component k hat. And so by the definition of the dot product that we looked at above, I can simplify the formula. It's just the integral I to f fx dx plus the integral from I to f fy dy plus the integral from I to f fz dz. And if you calculate these 3 separate integrals, you have calculated the work done by a force. Now again, this is all the theory that we need. Theory by itself makes very little impression. So let's look at a problem. The problem we're going to look at is this. And just to keep things simple, just like in that example, I went to 2D. Here also I will go to 2D, or 2 dimensions. So find the work done. Moving a particle from the point 1, 2 to the point 3, negative 5. Now one of the important things about the work done is you have to also specify the path in general. Later on in the course we'll find out situations where you don't have to specify the path, but right now you may have to along the path gamma 1 union gamma 2. And the path that I'm going to choose is this one, drawing here. x and y. So 1 comma 2 is somewhere here. I'm going to go straight down till I reach the point -5. So this point is 1 comma -5, and then I'm going to displace myself to the right by 2 units to get to my destination, which is 3 comma -5. This path down is called gamma 1, and that path is called gamma 2, and writing gamma 1 union gamma 2 simply means that you're looking at this path first and then that path. So well, that's one half of the story. I've still not told us what the force is, so let me just choose the following force as a function of x and y. I have two components only, x squared y I hat minus 2x y squared j hat. Okay, by the way, if I write f of x comma y, it doesn't mean I have two components. That just means that the force depends on two variables. I can again write a third component. For example, I could write e to the x times natural log of y z hat if I felt like doing, but I don't feel like dealing with that mess. So I'll just restrict to this. Now I'm going to use this protocol. Because this path is a straight line path, observe that if I go straight down, I'm keeping the x value constant. So on this path, dx is 0. Likewise, on this path, dy is 0. So we don't have to deal with much at all. Let's get going. So the work done by the force along the path gamma 1 will be the integral. Along the path gamma 1, x doesn't change, but y changes from 2 to -5. And only dy comes in, so I'm going to get f of y dy, and I have to make sure that the x value is kept at 1. So let's do everything. Integral from 2 to -5. The y component is -2 times x, but the x value is 1, times y squared dy. So I'll bring the -2 outside, so I'm going to get 2 to -5 y squared dy. The integral of y squared is y cubed upon 3. So I have to evaluate the integral from 2 to -5. So let me substitute the values and see what I get. I get -2/3. 5 cubed is -125, and 2 cubed is 8. So that's -133. And there's a negative sign up here, don't forget. -133 times -2 is positive 266/3 joules. The work done is measured in joules, so the unit joules are the same as newtons times meters, because force is measured in newtons and displacement is measured in meters. So that's the work done along path gamma 1. It's a positive work. Okay, now let's find the work done along path gamma 2, and then we'll add the two works up and we'll be done. Work done by the force along gamma 2. Along gamma 2, dy is 0, so the only contribution will come from dx. There's no d, this is dz. I wrote dy twice. Let me just correct that here. That is dz. It's a different kind of z, but we don't have z in this problem. So work done by the force F2. This time x will go from 1 to 3, but y will remain where it is. So that's going to be f of x dx. I'll only get the term fx dx because dy is 0 and dz is 0. At the value y equals -5, because y is staying -5 down there. Let's work it out. Fx is x squared y. So this is going to be the integral from 1 to 3 x squared, but the value of y is -5 dx. I'll pull out the -5 outside. Integral x squared is x cubed over 3 between 1 and 3, so that's negative 5 times 27, 5/3, 27 minus 1, which is 26. 26 times 10 is 260, so 26 times 5 is going to be half that, so it's negative 130 divided by 3 joules. This work is negative. Let's find the total work. Therefore, W net is going to be the sum of the two works, so WF gamma 1 plus WF gamma 2. I'm going to get 266 minus 130 divided by 3 joules, and that is what, 133 over 3. Is that right? 130 plus 133. Oh, sorry, 136. I don't know why that made that 36. So that's actually divisible by 3, if I'm not mistaken. Is it? Well, anyway, 266 minus 130 divided by 3. It's what it is. That's the answer.